Recording. All right. Hello. Welcome to Wednesday, everyone. Um, Course logistics things. I don't think there's much new to say besides, yeah, problem set is still due 2 days from today by midnight or by 11:59 p.m. So um, by this point, you should have already started working on it. I see a handful of submissions in Gradescope, which is great. Um, As a reminder, if you have questions, feel free to post them on Piazza. Feel free to come to office hours. Um, I think all the TA's office hours have now officially been posted, so um, that schedule should be there. Um, there's also the programming assignment, which is due uh, not this coming Monday, but the Monday after that. And as a reminder, you can submit a write-up for up to 10% extra credit on that. So there's a thing open on Brightspace for that. So you can just kind of like um, write a few paragraphs. There's some guidelines in the PDF and in the syllabus and stuff about what you might consider including in a write-up. Uh, but yeah, if you haven't already thought about that, maybe think about doing that. Um, yeah, cool. Okay, that's about all I have for course logistics. Does anyone have questions or concerns about anything before we jump into content? All right. If not, uh let's get into it. So, we yesterday we talked about the master theorem and about recursion and like designing recursive algorithms. I guess that was kind of continuing the discussion from Monday. Today, I hope to kind of wrap that up and then talk about dynamic programming a little bit. Um, And then if we have time, we'll start talking about trees, like binary trees. Um, and if not, that'll be Thursday and Friday, is we'll talk about binary trees. Um, Again, a reminder, I there's not going to be synchronous lectures next week, so the week of the 24th, um, because I'm not going to be in town. So I'll record some lectures ahead of time um, for you to watch. Uh, for the people who watch the recordings anyways, I guess that's not really going to be that much of a change, except for the fact that there's not like attendance polls for those asynchronous lectures. There's also likely not going to be an attendance poll today, um, just so you know. All right, it's cool that I said that and everyone didn't immediately drop out. So uh, thank you, I appreciate it. Um, okay, yeah. So I know we kind of rushed through the end of the master theorem stuff yesterday. Um, so I figure maybe we can start by like going back over that um, a little bit more slowly and kind of making sure that everything makes sense. Asynchronous lectures, I am just going to post them all at once. We're going to cover sorting algorithms most likely, so I'm just going to record a lecture for each sorting algorithm that we're going to talk about, and then just upload them all to Brightspace, and then you can kind of watch them at your own pace. Um, yeah. Okay. Let me show my screen. All right. I think it's visible. Okay, so this is again sort of a review from the end of last time, but since we went through it kind of fast, I figured it would be nice to go through it again a little bit slower. Okay, so last time we were talking about our pull up the chat window so I can make sure I can see what's going on. Great. Okay. Yeah. So last time we were talking about our maximal subarray problem, and we came up with a recursive like divide and conquer algorithm to write this. And then we were trying to understand the complexity of this algorithm, like how efficient is it? Is it better than the naive like O of n squared approach that we could use? Um, and we kind of uh, did some like heuristics and like vibe based estimations, and just kind of looking at the shape of the thing, and guessed that it would look like O of n log n, which is certainly better than n squared. Um, but the master theorem is sort of a uh, way to put all of those intuitions and all of those guesses together and kind of not have to prove the complexity every single time from scratch by hand, right? So yeah, puts the intuition that we've been building, I guess, past few slides yesterday, into a rule for guessing the form of the solution. So if you remember, the master theorem starts with a recurrence relation that looks like this. So it has to be a recursive calls, dividing the input size by b each time, and then you can do some f of n work inside each recursive call. So there's this extra like theta of f of n term. And then it breaks it into three cases. So it looks at the case where well, it basically it breaks the extra work that you're doing into three cases. So this f of n, if f of n is bounded from above by this n to the log base b of a. Um, so actually, I guess the way to think about this is if we just look at the recursive part, a times t of n over b, then the complexity of that is going to end up looking like n to the power of this like critical threshold, right? So maybe I'll call it c or something, right? Like n to the power c. So if f grows strictly slower than n to the critical threshold, n to the c, right? If f grows strictly slower than that, and in particular it grows polynomially slower than that, then we can ignore it, right? It's not going to affect the overall complexity enough, um, because right, like big O only cares about the highest order terms, and so big theta only cares about the highest order terms. And so the only thing we're going to end up with is this n to the log base b of a, right? N to the c. It's going to be polynomial. That's the first case. The third case is if f grows strictly faster than n to the log base b of a, right? That's why we've got the plus epsilon there. And again, it's polynomially faster, right? So if f grows sufficiently faster than the polynomial that we get by just unfolding the recursion, then unfolding the recursion is not going to be the hard part of this. The extra work that we're doing in every step is going to be the sort of like the dominating term, right? And so the final complexity we're going to get is just f of n. And then there's that middle case where f is tightly bound by that polynomial, right? So we do some recursion that gives us some polynomial n to the c, and then we also do some extra work that looks like n to the c. And so we're going to pick up that extra like log n factor, because the depth is going to be roughly log n. And then we're doing f work at each depth, and so we're going to pick up this like n to the c times log n. And so that's going to end up mattering. All right. So those are the three cases to think about for the master theorem. In practice, you can probably just look this up. The problem set for next week is going to have a bunch of practice problems. It's going to have a bunch of like problems related to the master theorem. So hopefully that should give you a little bit more practice and like a little bit more comfort with applying it. In particular, the master theorem doesn't apply in these three circumstances, right? So the attendance poll from yesterday was like, what are some examples of functions that aren't polynomially bound? And maybe we can work through one of these examples here. But yeah, so if the recurrence relation doesn't look like spawning a bunch of recursive calls, and each recursive call divides the input size by a certain amount, then we can't really apply it because this like log factor kind of goes away. So for example, for Fibonacci, we have like f of n minus 1 plus f of n minus 2. Um, and those aren't dividing it by a constant, right? So we can't apply the master theorem there. Also, if A or B are not constants. So if I, for example, if I have like an array of size n and the number of recursive calls I decide to split this into is something like the square root of n, right? Um, A is no longer a constant. A now depends on n. And so I can't apply the master theorem. The proof just doesn't work. And then finally, f of n isn't bound polynomially. So the example or an example. So actually this polynomial bound kind of depends on what our critical threshold looks like, right? So if I let me maybe try to okay, perfect. Okay, so if let's say like a equals 2 and b equals 2, which is the case for our maximal subarray problem, right? So I'm going to define c equals log base b a, which is just 1. So the critical thing that I care about is n to the c, which is just n, right? So a certain function f might apply if this were n squared or if this were constant or something like that, but not if it's just n, right? So for example, we look at f of n equals n log n, right? Can we find a value of epsilon such that, so I mean, intuitively, n log n grows faster than n, right? And so we expect f to be bound from below by n, right? So we expect to be in this third case if we're in any of the cases. Does everyone believe me on that? Yes. Okay, great. Thank you. Um, yeah, okay. So we would expect to be in this third case. But in order to be in this third case, we have to be able to find some like extra epsilon here, right? And so um, we need to find some confused. Does it have to be bound from below or above by that? How is that not considered trivial? Okay, these are great questions. So so first of all, big O, right? If you remember from our big O lecture from like, was it Friday or Monday maybe? Or from our like asymptotic complexity lecture or whatever, right? Big O means that it's bound from above, right? I missed. I meant to, here we go. Yeah. This means it's bound from above. This means big omega means it's bound from below, and big theta means it's bound from both sides, right? So if you remember in like the definition, if f of n is big O of g of n, there's like a less than or equal to in the definition. And if it's big omega is the same thing, but it has a greater than or equal to. Um, so yeah, so we need to decide what direction it's bound in. N log n, intuitively, we expect it to grow faster than n, so we expect it to be bound from below by n, which means we expect we expect to be in this third case. Big theta is both big O and big omega, right? So it's bound, it's a tight bound. It's bound from both below and above. Um, yeah. So maybe like for example, n squared equals big O of n cubed, and n squared equals big omega of n, because n squared is at least as slow it is no faster than n cubed, and it's at least as fast as n. But neither of these is actually what we care about. And so we want n squared equals big theta of n squared, right? Um, okay, let me erase some of this. Okay, so to answer the question about whether like isn't finding such an epsilon, shouldn't that be trivial? Um, that is kind of the issue here, right? So we want to find some epsilon such that n log n is less than or equal to n to, so this is going to be 1, so n to the 1 plus epsilon, right? If we, is that what I want? No, greater than or equal to, sorry, I mixed this up. Don't do what I did. Be better. Greater than or equal to. Okay. Um, so, right, so we want to find some epsilon such that n log n is greater or equal to n to the power 1 plus epsilon, right? This normally is not something that you'll have to work through by hand. You just have to sort of convince yourself that it's possible to do this. I'm hoping to prove to you that in this particular case, it's not possible, right? So we cancel out the n from both sides. We need to find, we get rid of this 1, and so we need to find some epsilon such that log n is like asymptotically faster than n to the epsilon. The problem is log n is always going to be slower than any polynomial, right? Even if we picked like epsilon equals 0.0001, right? Um, initially, this is going to be very, very slow, but eventually the polynomial is going to pick up and it's gonna overtake log n, right? So we can't ever find an epsilon that's so small that it gives us a polynomial that's slower than a log, right? Um, so that's sort of the issue, right? Um, on the other hand, if this were like, so it's not that n log n is a bad function, right? I think that's maybe the important thing that I want to draw attention to here, because if f of n were instead, let's say n squared log n, right? Then there's no problem, right? F of n is n squared log n. It's still bound from below by n because we expect n squared log n to grow faster. But now our problem becomes n log n is greater than or equal to n to the epsilon, right? Because we had n squared log n is greater than or equal to n to the like epsilon plus 1. We cancel out the squared here. We cancel out the 1 here. And now we need to find some polynomial that grows slower than n log n. And that's easy, right? N grows slower than n log n. And so we can just set epsilon equal to 1, for example, and then that's fine, right? So whether or not f of n, whether or not the master theorem applies doesn't only depend on what f of n looks like. It depends on how far f of n is from what the polynomial is going to end up looking like, right? From what n to the c is or n to the log base b of a is, right? So you do have to do a little bit of work to convince yourself that it grows sufficiently faster or sufficiently slower for you to be able to find some like polynomial in between. I guess that's the thing there. Uh, cool. Um, yeah. From the attendance poll yesterday, I also saw a handful of answers. So, okay, so first of all, right, attendance polls, these are just based on completion or effort. So even if you get the wrong answer, like it's fine. It doesn't really matter. It's more for me to know what things I should cover in a little bit more detail. So another common like sort of answer that I found was something like f of n equals 2 to the n, right? And as I mentioned before, um, this isn't bound. So I guess bound is a tricky word to say, right? Because 2 to the n intuitively is not bound by any polynomial. Because when we think of bound, we assume it's going to be like bound from above. But it is bound from below by any polynomial, right? So like even if log base b of a is like 100, right? N to the 100 is still going to be less than or equal to 2 to the n. Like we can always find constants that we can plug into this. to make this work, right? So 2 to the n is actually guaranteed to be an easy case, right? Because it's always going to be faster than any polynomial. And so in particular, we're always going to be able to make the third case work, right? The ones where you have to be careful is when f of n isn't quite a polynomial, but it's like something, it's like there's like a log there, right? Yeah, same thing with n factorial, right? If f of n equals n factorial, it's still bound from below, right? Like n to the 10th is still less than or equal to n factorial, right? Or like maybe I can say n factorial is still big omega of n to the 1 million, right? Um, so functions that like definitely grow really, really fast are not the issue. Functions that also grow really, really slow are usually not the issue. It's functions that are like somewhere in between, right? If you've got enough n's to cancel out the polynomial part, and then you have to like reason about whether you can get some polynomial to like make up for that log difference, that's when it becomes a problem. Um, so yeah, just something to know in general, like something to think about when worrying about whether or not you can apply the master theorem. And then of course the other cases, like if a isn't a constant, then it doesn't apply, right? So if my recurrence relation looks something like t of n equals like 2 to the n t of n over 2 plus n log n or something like that, right? There isn't a constant here. So I can't really do like log base 2 of 2 to the, I mean, I guess I could do log base 2 of 2 to the n, but um, the master theorem doesn't apply in those cases, right? And the reason is basically like the way you go about proving each of these three cases depends on these being constants. If you want to look at the proof, you can look up the proof, but I'm not going to talk about the proof here because this isn't a discrete math class. Yeah, okay. I think that's pretty much all I want to say about the master theorem. Does that make sense? Are there questions about that? I know that this is kind of like a complicated thing to sometimes understand. The first time I learned about this, it took me like multiple tries to kind of like wrap my mind around it because it's weird with like all the different cases and like memorizing what works and what doesn't. So I am happy to answer any like questions or like clarify anything about this if there's any questions. Yes, what's up? What are we supposed to do for epsilon? Um, you don't need you don't need to plug in a value of epsilon to apply the master theorem or to like get a result from the master theorem. You just have to know that it's possible to find an epsilon, right? So you'll notice like epsilon doesn't show up in these answers here, right? Once you pick a case, you just need to know that it's possible. Like if you pick the first case or the third case, you just need to know that the difference is enough that there is some epsilon that fits in between, right? So like I said, if f of n is like n squared log n, right? And this thing is you're trying to fit it into like big omega of n to the 1 plus epsilon, right? It doesn't matter what the actual value of epsilon is because we don't use it, right? We just need to know that it is possible to pick some epsilon. Like we just need to know that it's that the difference between n and n squared log n is at least some kind of polynomial, right? Also worth noting, epsilon doesn't have to be an integer, right? We could pick like 0.1 and that's fine. It's just if the difference is just log n, like there isn't an n squared here, if the difference is just log n, then there's no possible like exponent that we could put on n that would make it grow slow enough to be slower than log n, right? Because log n is slower than every possible n to the k. So exactly, yes, you do this to be sure that it's bound by f of n, or to be sure that f of n is bound from above or below by n to the c. Yeah, you don't actually like you don't have to worry about picking the wrong value of epsilon, right? As long as you look at it and you go, yeah, it's possible to find some epsilon, that's fine, right? And in general, you don't really have to like justify your choice of epsilon or whatever. Yeah, good question. Any other questions? Do people want me to work through an example with a different recurrence relation? Or, okay, great. All right, I will do that. I will do that on Zoom's whiteboard actually, so that I don't have to find space on my slides. Okay, so this, uh, I'm just drawing example problems um, from the textbook, from, what is this, Intro to Algorithms. Um, so yeah, okay. Let's see. Let's say we've got the recurrence relation. By the way, the whiteboard is visible to everyone, right? If I scribble over here, people can see it. Turn my mouse off. Okay, sweet. Okay. All right. So let's take a look at something that looks like T of n equals 2t of n over 4 plus the square root of n, right? Um, you can imagine that we're doing some like square root of n worth of work in some loop, right? Maybe we're, I don't know, counting up to the square root to check for like primality or something. I don't know. And then we're splitting the input into four equal chunks and then spawning off two recursive calls, right? Um, but like it doesn't matter what the algorithm looks like. What matters is that this is the recurrence relation that we get to describe it. So maybe I'll make this a little bit more interactive. First of all, do we have constants for A and B? Like, does this have the right shape to be able to apply the master theorem without worrying about whether we have good enough bounds on f of n? Yes, it does. Great. Okay. So if I write down my, pick a different color. Here we go. If I write down what the shape needs to look like, T of n equals A times T of n over B plus, I'll just say f of n. Okay, right. So we have a value for A, right? What's A? X2. Do we have a value for B? B is 4. And then f of n is, what's f of n? Yeah, square root of n. Right, there we go. Okay, great. Okay, so, okay, what's the next thing we need to do? We need to compute our sort of critical, yes, thank you. We need to compute our critical exponent, right? So log base b of a equals, what is that, log base 4 of 2, right? Which is what? 0.5? Yep. Okay. And actually for this, I think you're right. Writing it as instead of writing square root of n, it might be better to just write n to the 0.5 because I don't know, that might foreshadow the thing a little bit better. 0.5. There we go. Okay. So our the recursion polynomial looks like n to the log base b of a, right? Which in this case is going to be n to the 0.5. If we compare f of n to this, what case do we expect to be in? Uh, Maybe I'll remind you that the three cases are yes, it's the middle case, right? Right? So f of n is either big O of n to the zero point 0.5 minus something, or it's big omega of n to the zero point 0.5 plus something, or it's tightly bound by n to the 0.5. In this case, f of n is n to the 0.5, right? So we can comfortably say that we're in the middle case, right? Um, so if we're in the middle case, then our closed form solution for our recurrence relation is just, does anyone remember what this looks like? I can sort of cheat because I have my slides open, but does anyone remember what we get for this? If not, it's okay. Yeah, it's the n log n one, except it's the n to the 0.5, right? So it's the square root of n times the log of n, right? And so that gives us a closed form solution for our original thing here, right? And kind of the thing to think about, I guess, is like, or the intuition for this or whatever is like we're splitting the input into four pieces and only using two of them. So effectively, we're like we should pick up like a half somewhere, right? And so there's this like 0.5 going on, but we're doing this extra bit of square root of n work. And so when we get to this like depth of log n, right, if we're dividing the input into four pieces, then the total depth is going to be log base 4 of n. And so we're going to pick up this like factor of square root of n log n, or square root of n times log n. Um, and that's the thing that's going to dominate. So that's the result we get. Does that make sense? Does that example help? Do we want to work through another one, or are we kind of good with this? Another one would be cool. All right, let's do another one. Yeah, I'm gonna leave uh the like the shape and stuff up so that I don't have to rewrite that. Okay. Here we go. Here we go. Okay. So let's look at T of n equals. Yeah, here we go. So the first part of this is going to look kind of similar. N over 4 plus n. Okay. So first of all, does this have the right shape to apply the master theorem? And if so, what do our constants look like? Anyone have thoughts? So we have a constant for A, right? We have a constant for B, and then we've got some f of n here. So we can say A equals 2 as before, B equals 4, same as before, right? Because we're creating two recursive calls in each case. We're dividing the input size by 4 each time. And then the extra work that we have to do, f of n equals n, right? And so we plug a, b, and f of n into this, we get back the recurrence relation that we're looking at, right? So we just kind of pattern match. Does that make sense? Is everyone sufficiently convinced of that? Okay, let's keep going. The next thing we need to do is compute the critical polynomial, right? So as before, that's n to the power log base b of a, which is, if we look at log base b of a, log base 4 of 2 equals 0.5, right? As before, this is n to the 0.5. Okay, now if I've got f of n equals n, which case do I expect to be in? Let me pull up the three cases here. Is it 1, 2, or 3? We'll number them. Okay, I hear a 1. So 1 means that f of n grows, is bounded from above by this, right? Does everyone agree? Or does anyone think it's something different? I hear a 3. Okay, two conflicting answers. Which is it? Ah, all right. Aryan says 2. Okay, so now we've got all possible answers. Okay. It turns out to be 3, right? Case 3. Because or wait, yeah. Exactly. Yeah, bound from below, right? So our critical polynomial is something that looks like this, right? It's like a square root. And then f of n is something that looks like this, right? If you pretend that's a straight line. And so yeah, f of n is bound from below, right? And so we're in this third case. Okay, and so now Sid kind of said this already, but if we look at our if we try to plug in a value for epsilon, we need to find um, uh, n equals n is bound from below, so n is greater than or equal to, yeah, exactly. We're looking at the conditions on f of n, not the other way around, right? So 0.5 plus epsilon. And so any epsilon that's between um, 0, well, epsilon has to be greater than 0, first of all. I guess I should say that, right? Otherwise, kind of becomes stupid. Um, any epsilon that's between 0 and 0.5 is going to work, right? So for example, we could say epsilon equals 0.1, and so we get n grows faster than n to the 0.5 plus 0.1 is 0.6, and that's fine, right? And so the fact that we can find an epsilon means that this third case works. And so if the third case works, then the uh, the the complexity we get is, if we're in the third case, that means f of n is dominating, right? Because the third case says f of n is really fast. And so if f of n dominates, then f of n is the thing that's going to give us our complexity. And so our overall complexity is going to be theta of f of n, which is just theta of n. right? So even though we're doing some recursion here, um, the recursion is not contributing enough to to the um, to the overall like asymptotic behavior. And so the thing that's going to dominate is this n piece. And so we're going to get theta then. Does that make sense? Excellent. Thank you. I I guess I shouldn't admit this, but I cannot see who wrote the yes. Uh, I mentioned this the first time that I used the whiteboard. I don't know how to make it so that you all can't write on the whiteboard while I'm writing. Um, so thank you for saying yes. Um, understand that there is no accountability for this, but also please do not in general deface the whiteboard while I'm writing. Okay, great. We're gonna close the whiteboard then. So we've done an example with the middle case where we don't have to worry about epsilon. We've done an example where we do have to worry about epsilon. I've kind of looked at some examples where the master theorem doesn't apply. You will get plenty more practice on an upcoming problem set. So, okay, with that out of the way, let's talk about. I can't believe I thought I was going to get to binary trees today. Uh, okay, that means my prepared material lasts a little bit longer, and that is actually fantastic for me because it means I have to do less work. Okay, let's talk about dynamic programming a little bit more. I'm going to go back to sharing my slides. Here we go. Chat. I can see it. Okay, great. All right. So, dynamic programming algorithms. We've talked about this before, right? A little bit. I want to kind of go into a little bit more detail about this and then maybe like work through an example, although we might not have time for the actual example. So maybe we'll just kind of do this at a high level. Okay, so dynamic programming. Often, this is a dynamic programming algorithm is something that will apply to an optimization problem. Um, so normally with our algorithm so far, we've thought about like we want to compute a particular result, right? We want to like compute, um, I don't know, the depth of a binary tree or like the nth Fibonacci number or something like that. But for example, with our maximal subarray thing, what we have is like a space of possible solutions, right? There's um, there's a space of possible like subarrays. Given some array, there's a space of possible subarrays. And this is what's parameterized by the input size, right? A lot of times this will be like um, on an input size of n, there's n squared possible subarrays, or there might be like n squared or like 2 to the n subsets, right? Or like something like this, right? So we have a space of possible solutions, and then we have some objective function that tells us how good a particular solution is. So for our maximal subarray problem, we cared about our objective function was basically like given a subarray, how high can we make the sum of the elements, right? And so we want to find an element in that solution space that in this case maximizes, it could also be minimizes some particular objective function, right? Um, that's the general idea of optimization problems. It turns out a lot of things that you want to do in practice can be framed as some sort of optimization problem, right? Um, you've got like all possible solutions that you might care about, and then some solutions are better than others, and so you try to like optimize with respect to how good the solution is, and you try to find a good answer. Um, so yeah, uh, divide and conquer is a very powerful strategy for thinking about algorithms, for like designing like conceptually designing an algorithm that solves a problem. Um, if we want to apply a divide and conquer approach, there's two sort of conditions that have to be met. First of all, an optimal solution is also optimal within, or I guess I guess these are kind of saying the same thing, right? An optimal solution to the full problem has to induce optimal solutions on each subproblem, right? So in the case of the maximal subarray, if we have if our subproblems look like taking the whole array and breaking it into two pieces, like looking at the left half and the right half, um, if something is maximal, if an array, if a subarray is maximal, like if we've already found the best possible subarray on the whole thing, it necessarily also has to be the best possible one just in the left half, right? So if there was something better in the left half, it would automatically be better for the whole thing, right? So this sort of tells us that it's okay to like break things down and look at what and like optimize in each like smaller piece, right? So in general, the divide and conquer strategy says we take our problem, we break it into subproblems, we optimize within each subproblem, and then we combine these optimal solutions to get some solution for the original problem that we cared about, right? Um, there's some you can be kind of precise about when this works and when like a greedy algorithm is fine. We'll maybe talk about that at the end of the semester. This is not like part of the this is not required material for the course. I just think it's interesting. There's a structure called a matroid, and if you can show that your problem exhibits this matroid structure, then you're guaranteed that a greedy algorithm is going to be optimal. But anyway, so this is our sort of divide and conquer strategy. We talked about this for maximal subarray, right? This is how we computed our thing. The trouble is, if we're splitting into a bunch of like smaller subproblems, and our subproblems aren't necessarily like half the size, right? We end up with something that looks like an exponential complexity, right? We get a recurrence relation that looks like T of n equals alpha times T of n minus k, and so we get a depth that looks like O of n, and so we get something that looks like alpha to the O of n. This is an exponential complexity, and that's not great. In fact, if the solution space itself isn't exponential, right? If the like space of things that we're exploring is not exponential, then there's a good indicator here that this exponential amount of work that we're doing is like solving the same subproblems over and over and over again, right? So going back to our Fibonacci example, Fibonacci looks exactly like this, right? It's like T of n equals 2 times T of n minus 1, which is exponential. But there's only n Fibonacci numbers, right? So if we have to take two to the n steps, if we have to take an exponential number of steps just to compute a linear number of like things, like visit a linear number of states, then chances are we're visiting the same state over and over and over again, right? So that is a place that we can look at to sort of try to optimize our algorithm a little bit, right? I'm going to pull up an explicit example here. This is the rod cutting example. Okay, so the sort of the setup here is the amount that someone's willing to pay for length of rod is often not proportional to the length, right? So you might pay $1 for 1 foot, $5 for 2 feet instead of just two, $8 for 3 feet, $9 for 4 feet. This is an example like that maps lengths to prices, right? The problem, the rod cutting problem is given a length, how do we break it up optimally to sort of like maximize the amount that we can sell it for? And the trick here is we're only allowed to break it in like integer segments because otherwise this is kind of dumb, right? We can only sell an integer length of rod, right? So for example, if I've got a 4-foot rod, I can sell it as is for $9, or I can break it into 4 1-foot pieces and sell it for $4, or I can break it into 2 halves of 2 feet each and sell it for 5 plus 5 is 10, or I can break it into a 3 and a 1, which is 9, right? So obviously, and these are all possible ways that I can break down a 4-foot rod, right? There's no other like a 1 and a 3 is the same thing as a 3 and a 1, for example, right? So yeah, if I look at all of these, I can enumerate all of the possible solutions. I can look at these and say, okay, well, $10 is the best. And so the best thing to do here is to sell it as 2 foot long rods, right? So the optimal solution is to break it into 2, 2. But how do we know, right? So as I said, the brute force solution is like just try every possible way of cutting the rod. And naively, this ends up looking something like e to the square root of n over n, right? I'm not going to try to prove this, but this is sort of you can look like the Catalan numbers is what this ends up being, and some like combinatorial choice problem, and it's yeah, it ends up looking like e to the square root of n. The point is it's exponential, right? Which is bad. And so let's try to design a recursive algorithm. It now occurs to me I did not put separate builds into here, so you can just like see all of the answers. That's fine. Okay, if we're converting this into a recursive algorithm, we need a base case and we need subproblems, right? I guess I'm just going to say this because if I asked you, you would just like, I would just be asking you to read off the slides and like read to me. And I don't think there's much value in that. But it's maybe worth like thinking about this on your own and like trying to convince yourself that you would arrive at the same answer as I have written down here. But the base case is if we have a 1 foot rod, it's indivisible, right? We can't break it into like half a foot, right? So we have to sell it as is. There's only one option. And so that's sort of like trivial, easy to compute, right? Um, and then the subproblems that we have, if we have, let's say, a rod of length n feet, and we decide for sure that we're going to have a k foot piece in there, then um, we have a smaller rod of size n minus k that we can now worry about optimally subdividing, right? This is a smaller subproblem. And eventually, if I keep like tearing off chunks, eventually I'm going to get down to something that's indivisible, right? And so I know that eventually I'm going to hit the base case and my recursion is going to terminate. And also, an optimal subdivision of the rod necessarily gives you an optimal subdivision of the union of some of the pieces. Uh, that is, maybe I should explain what I mean by that. Also here, I meant to do some live coding. Honestly, I think we're just going to do the live coding portion of this tomorrow. So uh, at that point, it's probably worth starting this part over tomorrow. And so in that case, I think I might call class a little bit early here. Yeah, easy lecture, hopefully. Easy lecture in the sense that there's not as much content. Also, there's no like attendance poll, so you don't have to worry about that. Uh, yeah, great. If you have questions, feel free to stick around. I'll answer them. If you want to stick around and see if other people have questions, feel free to do that as well. Otherwise, you are free to go. Bye.